But here is the NearSpec MOS pipeline notebook. And what a brief overview of what we're going to be doing. I sort of showed this before. We're going to be going from the, I think we actually start from the uncals. This is showing the rate file, and then we'll generate the S2Ds and the X1D. And this is just to show what it looks like. This image here will come in the third notebook that I'll show. But this is just to show the particular object that I'll be demonstrating here. Actually has 5 slitlets, so it confused the automatic 1D extraction. So that's one of the key improvements I'll show, is just being able to tweak which rows we extract. But it's the standard 3 slitlet nodes, just with the extra slit there. So this is where we're heading with this notebook. And so here it is. We have an overview, and then we go into the various steps of the pipeline here. And I won't go into everything in detail, but again, this is from the ERO program. A little bit of background about that, and the particular galaxy we're going to be focusing on here. So a bit of background about the JWST pipeline, and the various stages and the outputs that come from each. I summarize here. And some links to related notebooks. The last time we did one of these on the NearSpec MOS pipeline was I think 2 years ago, before there was real data coming out. So it's it's about time we do one of these for you, and we're happy to show this today, and just in time for all the good improvements we have. All right, so we start out by importing some libraries, and it's important to do these next few cells in order. I've done it wrong all the different ways you can, and it breaks in various ways. But the first thing you want to do is set your CRDS path. So these are for the calibration files that will be automatically downloaded. You might do this in your shell, but here I do it explicitly in the notebook. Then you're going to import CRDS, and if you're online, it'll tell you what PMAP you're using here. And then you import the JWST pipeline. And here we're using the latest version 1.14. Then if you want to do things on multiple processors to speed things up, you can set that here. To retrieve data from MAST in the notebook, you can use Astro Query. And then here's for plotting and a few other helper functions. Now here's where you might want to start. This is you're going to define your download directory for the data as it comes down from MAST, and then a separate directory where you're going to reprocess the data. Now here I've set run pipeline to false. I'm just going to go through and display a lot of the results, but you would set that to true if you're actually running the pipeline. And as I mentioned, this takes a little while. So the entire thing would take, it took about 75 minutes on my laptop. So we're not going to run it in real time here, but yeah, I'll just show you what the outputs are. All right, so we're going to start with the uncal files from MAST. And I showed you the outlier rejection is pretty good these days. You could start with the rate or whichever stage you wish, but here we're going to start with those uncal files. So here's a helper file, a function to download those files. And another one just to help download large files with a progress bar. And a few more helper functions there to select a subset of those files. I'm not going to show Astro Query here, but there is a block of code that does that. The output is a bit long, but this is how you query MAST right here in the browser with the proposal ID, and you can select various things. Here we're going to look at the G395M observations from this ERO program. But here I've already figured out which files they are, and it doesn't show up here, but it'll show up down below. So now we're on to stage 1 of the pipeline. There's a lot more detail you can find on read the docs. And in particular, how to change these parameters are found on these individual pages. So for example, if you go to the jump step page, you'll see that the various arguments are all listed there. Here, we're just gonna change a few of them. So these were parameters that were recommended by the Sears team based on their experience with the near-spec data. As I showed, the automated snowball rejection works pretty well, but we're going to use the Sears parameters here. We're also going to use multiple cores, about half the cores on the system, and yeah, also for the ramp fitting. So here we run detector one pipeline, and I cleared the output because it's very long, as you're probably familiar with. Yeah, that's where you run it, and if you want to see the results in detail, they're included here. The next thing we're going to do is going to show the results. So we ran stage one, so we're going to get a rate file out. So we have this helper function to show that, along with the extraction regions. And so this is the reprocessed file. I've went ahead and ran it, and it's on box here if you want to see the output that I got. And here it is. So this is what I showed before in the intro, so it looks pretty good. And there's some striping that NSClean can take care of that Kaylee will show in one of the next notebooks that I didn't run here. It's NSClean isn't on by default. You have to turn that on if you want to use it. And now we're going to compare it to the data straight from MAST. So we know the name of the file, so we can download it here simply. In this case, my function knows that it already is on the machine, so it just loads it, and here it is. So as I showed before, if you go back and forth, these look pretty similar now with all the latest pipeline and calibration updates. All right, so now we're on to stage two. So here we're going to just process that one rate file, but you could batch run through all of them if you have them. And this is for observation 7, and we also need the association file. In this case, since we're just doing the one rate file, the association file is simple. It just has one file in it. And so you could download it from MAST, or here we're going to create it from scratch. So here for spec 2, it's pretty simple. In spec 3, it'll be a little more involved, as you'll see. But so we just define which rate files go into it. Yeah, as I mentioned, stage 2 just works on one detector at a time. And so there's just the one rate file and the association file. And this just shows what the content of that association file. I believe you can run it just on the rate file itself too, but here we're running it on the association file. All right, the next thing you'll need is the MSA Metafile. In my next notebook, I'll go into detail about what that is. But for now, just know that you need to download it. It defines where the shutters are and which sources are in them. And so it's in the FITS header of, I think, pretty much all the files. So here we'll get it from the rate file. It's in the FITS header here. And one of the things I should mention is that you can open these files with just the standard FITS libraries. I think this is from AstroPi, or the data models, which are also very useful, give you access to more useful stuff. All right, so now that we have everything, we're on to stage 2. Again, there's a lot of details on the various parameters and things you can change. Here we're just going to change this one, the weight type for the resampling. IVM does a bit better at rejecting outliers, although EXP time is now the new default, improving the signal to noise, especially for bright objects. A bit of a trade-off there. So here we run spec 2. Again, I've cleared the output because it's a lot, but this is where you would actually run it. And now we're going to draw those boxes. We're going to show. So once you run stage 2, it does all the extractions. So we'll show where it actually does those. So this is one of the outputs from stage 2 is the cal file. So again, I've staged it on box here, and you can see my output. And here we're just going to use the cal model, the data model of the cal file to show where those extractions were. So here it's just showing these rectangles as where we get those 2D extractions. And I should have mentioned here in the middle is that light coming in from the fixed slits. And I believe also the IFU comes in there. Is that right? Maybe not. Fix Slits anyway. All right. So here for stage 3, we are now we have to now we're going to combine all the different exposures into one. So now we have to make the first step is to make an association file, and so we'll have here we're just going to go ahead and download that association file from MAST. So the which file it is in the header, and so yeah, this shows how to download it here. Here I guess here we actually we go to MAST and we query it, and then we find the association file in there and we select it. It's the one with spec3 in the name, in the file name. And this is just showing the contents. It's these 6 different files. So the 2 different detectors, and then the 3 exposures for the knot. And then just in a little bit more detail what's in there. And you see the various nods there. It also has the target acquisition in there, which I'm not sure if it's actually necessary, but anyway, it's in there. All right, then we finally get on to run spec3. Here we're going to change a few of the parameters. We're going to make sure we do the outlier detection. We're going to set that weight type to IVM again. And we're going to make sure to use the source position for the 1D extraction. This might be on by default, and I'll also add that this has been improved a lot in recently, so it works a lot better than it used to. Here's where we actually run spec3, and now we'll again I cleared the output, and we'll show the result. So nice helper function there. Let's pick which source to show here. And then it'll download the file. Here again, I'm showing the output that I've done, and they're here on box. And here, right, we load these into data models. So for the S2D and the X1D files. The data models have a lot of useful information that you could show all of the info if you want. I'm not going to do that here. But here is the final result. And we have the S2D and the X1D. They're on the same wavelength axis. So we've gotten that from the X1D, and we show it alongside the S2D here. I've also expanded out this wavelength gap, which isn't in the data itself. Right. And I should emphasize that this isn't necessarily linear. It's whatever the pixel data are is what we're plotting here. But in this case, it's close to it. For the prism, it varies more as you go across the wavelength. All right, now for the final step, we're going to adjust that 1D extraction because it didn't quite get it right. And so what we're going to do is there's not a simple way to do this in terms of setting parameters, but it's not that bad. You just have to use this reference file and change the parameters in the file as input to the pipeline. So again, you could download the reference file, this extract1D JSON file. But here we're going to go ahead and create it from scratch. The file isn't that complicated, and I show how to do it here. And these are the contents. Just has a little bit of content here. The main thing we're going to change now is the extraction width to 6. And this is actually the new default. It was 8 up until recently. And here's the other. All right, so this is how it. This is the default parameters, and here we're actually going to change it a bit. So we're going to set the center. I just did this manually. You could be more sophisticated and figure out where that source is in your spectrum, which row. But here I just eyeballed it and pick row 25, and then also the extraction width explicitly here. So it'll do these rows inclusive. And here's where we actually write out that that JSON file. And here's the contents just to check. Now we'll run this. You can run this step independently without running any other parts of the pipeline. So it's pretty quick. And here I do actually show the results. And then now we're going to load that into a data model and show the result. So here it's doing a pretty good job. I show in pink is the extraction region I'm using now, and the gray dashed line is actually just a guess. I should have gone back and to see where it extracted from by default. I think that's going to be in the headers now. It wasn't for a while. It does show up in the pipeline as you run it, but it hasn't been in the headers up until recently. I think it's in there now. But I think it was a bit offset anyway. So this looks pretty good. Now let's compare to what you get just from Mast or from the default pipeline. So we know the file name. We're just going to download that from Mast with these functions, load them into data models, and we're going to do a slightly simpler plotting without all those helper functions. So you really just need a few lines of code to plot these up. And this is comparing what you get straight out of Mast and versus the reprocessed version that I showed above. So if you kind of zoom in here, you can see that the default extraction for this object missed the extraction. And if it were, again, this is with a 5-slitlet object or a definition that isn't really standard. For most of the objects, this would be a lot better, this comparison. And so I might have given credit to the default pipeline by showing a 3-slitlet, but I wanted to show more of an improvement here. And finally, we're going to compare it here. So this is what you get straight out of Mast in blue, and then if you reprocess it, is what you get in gray. And then when you move the extraction region to this red lines here, it's even better. So you can see the three compared there.